So, how do scientists actually find one specific tiny ingredient swimming in a huge sea of other chemicals? Well, they use this incredibly powerful technique called high performance liquid chromatography, or HPLC for short. Now, it sounds super complex, I know, but you can really think of it as a journey, like a microscopic obstacle course that we're going to send our molecules on. Okay, let's dive in and follow a sample from the very start to the very finish. All right, so here's our game plan. We're going to kick things off with the basics. What exactly is HPLC? Then we'll follow our sample as it gets pushed along by the system's engine, the pumps. We'll see it get introduced through the injector, race down the column, and finally, cross that finish line at the detector. Let's get started. So first up, what problem are we even trying to solve here? Well, at its core, HPLC is all about playing the role of the ultimate chemical detective. I mean, think about it. Imagine trying to figure out the exact amount of caffeine in your morning coffee, which has, I don't know, hundreds of other compounds floating around in it. Or maybe you're trying to find a minuscule trace of a pollutant in a water sample. How on earth do you pick out just one thing from that complex chemical soup? Well, that's precisely the question HPLC was built to answer. And here is the official textbook definition. HPLC is a technique that lets scientists separate, identify, and this is key, measure the amount of each component in a mixture. It literally takes a chemical jumble and turns it into clean, organized, understandable data. It is the go-to tool for pretty much everything, from making sure a new medicine is pure to checking if that organic label on your food is telling the truth. So let's quickly trace the path our sample is about to take. The whole process follows this exact sequence. It all begins with a liquid, which we call the mobile phase, because, it moves, that gets pulled from a reservoir by a really powerful pump. Then our sample gets introduced using an injector, and it's pushed into the column. Now, the column is where all the real separation magic happens. After that, a detector sees the components as they pop out the other side, and then everything finally ends up in a waste container. That's the journey we're about to explore, piece by piece. Okay, let's get into part 2 and see how this all kicks off. And it really starts with the engine of the entire system, the pump. The pump's job sounds simple, but it is absolutely critical. It grabs the solvent and shoves it through the system at a super precise and rock-steady flow rate. And it does this under some serious pressure. We're talking up to 15,000 pounds per square inch. That stability is everything, because it's what makes sure the results are reliable time after time. If that flow fluctuates even a tiny bit, the whole analysis can get thrown off. That consistent pressure is what gives us what we call reproducible retention times, which just means a certain chemical will always take the exact same amount of time to get through the system. Now, pumps can run in 2 different modes. The simpler one is called isocratic, where the solvent mix stays exactly the same the whole time. It's great for quick, simple analyses. But for the really complicated samples, analysts use gradient mode. This is where the pump actually changes the solvent mixture over the course of the run. This trick helps to separate compounds that are really similar, it gives you much sharper results, and believe it or not, it can often speed up the whole process. So how does a pump actually create that change ingredient? Well, there are 2 main designs. You've got a binary pump, which uses 2 separate pumps to mix 2 solvents together after they're already under high pressure. This is the best way to go for getting really high resolution. Then there's the quaternary pump, which is all about flexibility. It uses just 1 pump to mix up to 4 different solvents before they get pressurized. This gives you a ton of options when you're developing a new method. Okay, our mobile phase is flowing steadily. Now it's time to actually get our sample into the system. So let's look at the gateway, the sample injector. Injector technology has really come a long way. Back in the day, you'd basically just use a syringe and poke it through a rubber seal. As you can imagine, that was not very precise. Then came the stop flow injector, which was a step up, but it meant you had to completely stop the system's pressure, which was just a huge pain. Today, the undisputed champion is the Rheodion injector. It's an elegant solution that introduces the sample perfectly without ever missing a beat in the flow. And this is how that brilliant little device works. It's just a simple 2-position valve. In the load position, you fill a tiny loop with an extremely precise volume of your sample. All the while, the high-pressure mobile phase is just flowing right past it, completely undisturbed. Then you flick the switch, or the valve turns to inject. Instantly, the flow path is rerouted through that sample loop, and it cleanly sweeps your entire sample into the system and sends it on its way to the column. It's precise, it's reproducible, and honestly, it's just genius in its simplicity. All right, our sample is officially in the system and it's heading for the most important part of its entire journey, the racetrack. And that's the column. This is where the magic of separation really happens. So, inside this stainless steel tube, it's packed super tightly with these tiny particles. We call this the stationary phase because, well, it doesn't move. Now, as our moving liquid, the mobile phase, pushes the sample through, each chemical component in that sample is going to interact with these stationary particles a little bit differently. Some molecules are really attracted to the particles, so they get slowed down a lot. Others barely interact at all and just zip right on through. It's this difference in travel speed that separates the mixture into these neat, individual bands of molecules. Okay, so our components are now separated. They're coming out of the column one by one. But how do we actually see them? If you can't see it, did it even happen? This brings us to the finish line, the detector. The detector's whole job is to turn invisible chemicals into a signal we can read. And there are a bunch of different types, each one like a specialized camera. The most common one you'll run into is a UV vis detector, which is great at seeing compounds that absorb light. For finding things at super low concentrations, a fluorescence detector offers unbelievable sensitivity. Then, for things that are invisible to both of those, an ELSD or evaporative light scattering detector can often do the trick. And then, for when you need absolute certainty, there's mass spectrometry. And yeah, that brings us to the undisputed king of detectors. This quote right here really says it all. A mass spectrometer detector, or MS, doesn't just see a component, it positively identifies it by its molecular weight. It's basically putting the molecule on a scale to find its unique chemical fingerprint. It gives you unequivocal proof. In fields like pharmaceuticals or forensics, where you absolutely cannot be wrong, the MS detector is the gold standard, period. So there we have it. We've gone from a jumbled up sample to these clean, separated, and identified components. Let's just take a step back and recap the entire journey, from the solvent reservoir all the way to the final result. A really helpful way to think about the whole flow path is in terms of pressure. It starts out in a low pressure zone, from the solvent bottle right up to the pump. Then it enters the high pressure zone. That's everything from the pump's outlet through the injector and all the way through the column. And then finally, once it leaves the column, the pressure drops right back down again on its way to the detector and the waste. Honestly, understanding these zones is the secret to troubleshooting almost any problem you'll ever have with an HPLC system. So why does understanding this whole journey matter so much? Because every single step is a link in a chain. A stable flow from the pump is what allows for an accurate injection. An accurate injection is what leads to proper separation in the column. And proper separation is what allows for consistent detection. See? A problem in any one of those spots compromises the entire result. That's why having a really deep understanding of this flow path is the absolute key to getting reliable, reproducible results you can actually trust. HPLC has really given us this incredible window into the chemical world all around us, letting us pick apart molecules with just breathtaking precision, which, leads to one final thought. With this kind of analytical power at our fingertips, what are the next big challenges we're going to solve? What new discoveries are just sitting there waiting, just beyond the reach of today's technology?